Hello everyone, welcome to today's presentation on soil-water balance, part of our course on Basic Environmental Sciences. Maintaining a proper soil-water balance is essential for plant development and fitness, especially in semi-arid regions. It minimizes water losses and ensures efficient use of soil moisture, leading to better crop yields. Water also plays key roles in plant life, such as dissipating heat during metabolic activities, donating electrons in photosynthesis, and aiding in the circulation of nutrients. Understanding soil-water balance helps improve plant health and supports sustainable agriculture. This slide illustrates the soil-water balance equations, or SWBE, which are crucial for understanding the movement of water within the soil system. The soil-water balance diagram shows the inputs and outputs of water, helping us calculate the net water storage in the soil at any given time. Key components include P for precipitation, which is the primary source of water input. I represents irrigation inputs, which can be added to supplement natural rainfall. U is upward capillary flow, which brings water from deeper layers up to the root zone. All these three elements contribute to water inputs. While for water losses, E and T stand for evaporation and transpiration, respectively, collectively known as evapotranspiration. R indicates runoff, the water that flows over the soil surface and is lost. D represents drainage to groundwater, where water percolates down through the soil layers, and lastly, L is lateral groundwater flow, the horizontal movement of water through the soil. Hence, subtracting water inputs from water loss is equal to change in soil water storage. Understanding the soil-water balance is crucial for identifying periods of water stress or excess, which can negatively impact crop performance. By using the soil-water balance equation, we can detect when crops might face water shortages or oversupply, allowing for timely and effective management interventions. This knowledge enables us to adopt appropriate management practices, such as irrigation adjustments or drainage improvements, to alleviate these constraints and optimize crop yields, ultimately supporting more sustainable and productive agricultural systems.
Let's look at an example to apply the soil-water balance equation. We have a field where we're given various parameters over a period from August 1st to August 31st. The soil moisture at the beginning of the period, M1, is 300 millimeters. Precipitation or rainfall, P, recorded is 70 millimeters. There are no inputs from irrigation, I, or groundwater contribution, U, both listed as nil. Runoff, R, is recorded as 10 millimeters. Deep drainage, D, is also nil. By the end of the period, on August 31st, the soil moisture, M2, is measured at 250 millimeters. Using these values, we aim to estimate evapotranspiration, ET, over the month. This example will help us understand how changes in soil moisture levels can be analyzed using the soil-water balance equation to calculate ET, providing insights into water management for crop production. The equation we use is M1 plus P plus I plus U equals ET plus D plus R plus M2. Substituting the given values, initial soil moisture, M1, is 300 millimeters. Precipitation, P, is 70 millimeters. Irrigation, I, and upward capillary flow, U, are both 0. Runoff, R, is 10 millimeters, and deep drainage, D, is 0. Final soil moisture, M2, is 250 millimeters. We replace the values in the equation. 300 plus 70 plus 0 plus 0 equals ET plus O plus 10 plus 250. Simplifies to 370 equals ET plus 260. Solving for ET, we find ET equals 370 minus 260 equals 110 millimeter. So, the estimated evapotranspiration for the period is 110 millimeters. Let's move on to example 2 to apply the soil-water balance equation to estimate deep drainage, D, during a crop period. For this example, we have the following values. Initial soil moisture, M1, on June 10th is 150 millimeters. Precipitation or rainfall, P, over the period is 600 millimeters. There are no inputs from irrigation, I, or groundwater contribution, U, both listed as nil. Estimated evapotranspiration, ET, is 530 millimeters. Runoff, R, is recorded as 70 millimeters. The final soil moisture, M2, on September 30th is 60 millimeters. Using these parameters, our goal is to calculate the deep drainage, D, from the field during the crop period. This calculation helps us understand water losses beyond the root zone. Now, let's solve for deep drainage, D, using the soil-water balance equation from example 2. We use the equation M1 plus P plus I plus U equals ET plus D plus R plus M2. Substituting the values. Initial soil moisture, M1, is 150 millimeters. Precipitation, P, is 600 millimeters. Irrigation, I, and groundwater contribution, U, are both 0. Estimated evapotranspiration, ET, is 530 millimeters. Runoff, R, is 70 millimeters. Final soil moisture, M2, is 60 millimeters. 150 plus 600 plus 0 plus 0 equals 530 plus D plus 70 plus 60. This simplifies to 750 equals 660 plus D. Solving for D. D equals 750 minus 660 equals 90 millimeters. Thus, the deep drainage from the field during the crop period is 90 millimeters. Thank you for joining this session on soil-water balance. I hope you found the information useful in understanding how water management in soil impacts crop growth and sustainability. Your active participation is appreciated.